Good morning. So if you were watching this during our normal class time, I am probably in Minneapolis Airport waiting to get on a plane to come back home to Winnipeg. All's gone according to plan. So today's lecture will be delivered remotely and asynchronously. And rather than just give a standard lecture with no live component at all, figured I'd do this a little bit more like I would do a standard asynchronous course. So this lecture is going to come in 3 different parts. You can watch each of these parts back to back and it should all make sense, but if you want to take some time in between, that's totally fine. Altogether, the parts should fit into our regular lecture time. So this is part 1. And we're going to move on from what we were talking about before, which was counting, different methods of counting and combinatorial problems and proofs. And we're going to start talking about graph theory. So earlier in the course, we talked about sets. And sets are in some case the most simple structure that we can talk about. Sets are all about elements and just whether those elements belong or not. In fact, when we talked about sets, we very quickly stopped talking about the elements, and we were mostly worried about relations between different sets, because sets themselves are just so simple. And so if we go one step up in the power of the structure we're talking about, we get to graphs. So graphs informally are going to be about elements and how the elements are related to each other. So not just whether elements belong or not, but whether elements are related or not. So in some large sense, graphs are similar to sets, and we'll see that, in fact, a graph has a set inside of it, but is more focused on relationships than just elements themselves. So formally, I'll give you a definition. Formally, a graph is an ordered pair V comma E, where V is just a set. So like I said, graphs have sets inside of them. And we call everything in V a vertex, plural vertices. So V is a set of vertices. And E is a subset of the power set of V, where everything has size 2. So it's a subset of sets of elements of V of size 2. Okay. But this definition is really not how we think of graphs. So I want to give you an example of a graph. And normally when we draw graphs, we draw vertices as points and edges as lines between those points. So in this graph, my vertex V is going to be the set of provinces in Canada, or I should just say provinces of Canada, because I've already drawn my set symbol. And I'm going to draw an edge between 2 provinces if their postal abbreviations share a letter. I'm going to abbreviate abbreviations because, I mean, you kind of got to, right? Share a letter. Okay, let me do this on a new page just so I'm not running into space requirements. Okay, so let's start with Manitoba. Draw that vertex first. So we have MB. That's a vertex. And now any province that has an M in it or a B in it is going to be connected, is going to be adjacent to MB. There's an edge between Manitoba and any province that has a B in it, or an M. So there actually are no other provinces with M in their postal code, but there are some with B. So British Columbia is BC. Another one there. And Alberta is AB. And New Brunswick is NB. Okay. And now I can think about these. These are also all going to have edges between them because they all share a letter. So BC and AB share B. NB and AB share B. BC and NB. And now no other province has A in its abbreviation, but there is another province with a C in it. So Quebec is QC, so we get to add that edge there. And now there are a couple more provinces with N in it. So we have Ontario is ON, and Newfoundland and Labrador is NL, and Nova Scotia is NS. So I've drawn in those vertices and those edges. And now again, same thing as over here, Ontario and Newfoundland and Labrador both have N. Nova Scotia and Ontario both have N. Newfoundland and Labrador and Nova Scotia all have N. So I get all of those edges as well. No edge between Manitoba, Newfoundland, and Labrador because they don't overlap in letters at all. And then no other province has O, no other province has L, but there is another province with an S. That's Saskatchewan is SK. And then if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, we're missing one. Poor province that always gets forgotten. Prince Edward Island, PE. Even if you add the I for PEI. Doesn't get to be adjacent to anybody, just a vertex, no lines connecting it. So this graph represents this, or this picture represents this graph. Now the graph really is a set and a collection of subsets, right? This is just a representation of the graph, but the graph itself is the set QC, BC, MB, AB, NB, PE, ON, NL, NS, SK, and then the ordered pair, or the sets of size 2, the subsets of size 2, QC, BC, BC, AB, BC, MB, and so on for all of these different edges. By the way, I like this graph because it puts New Brunswick right at the heart of Canada. And I think that I don't know many New Brunswickers, but I imagine they'd like to think of themselves as right at the heart of Canada, because they don't often get to be. But this is just one way of drawing this graph. And because New Brunswick is right in the middle, it's kind of maybe a non-intuitive way. So I want to draw another way, a slightly more geographic way. So we could draw this graph roughly geographically. See how good my Canadian geography is. I'm going to cheat a little bit here and go just to fit everything on the page. All right, a very rough map of Canada, and I can draw the same edges in. Do them in a different color so it's clear where everything is. So BC is connected to AB and QC and MB and NB, and AB is connected to BC already, and also MB and NB, and MB is connected to NB, and then Ontario is connected to New Brunswick and Newfoundland and Labrador, and Nova Scotia, and Newfoundland and Labrador is also connected to Nova Scotia and New Brunswick, and Nova Scotia, I should be doing these in order. Quebec, already good. New Brunswick, I'm connected to Alberta and Manitoba and British Columbia already, and Ontario and Newfoundland and Labrador, and now I just need Nova Scotia. We're good. And then Saskatchewan connected to Nova Scotia. There we go. Okay. These are both pictures of this graph. They look very different, but the picture is not the graph. The graph is specifically this set and this collection of subsets of size 2. In particular, note that it's okay if our edges cross. We just have to be really clear that there's no vertex here. There's no secret province between Saskatchewan and Manitoba just because these two edges overlap. So as long as your picture is clear what a vertex is and where the edges are, we use pictures to represent graphs, but pictures are not graphs. Okay, let's talk a little bit more about graphs. There are lots of different variations on graphs. So everything I've done so far would be considered a simple graph, but I want to talk about some possible variations. One is a directed graph, or a digraph. Oops. Not spell. Digraph or directed graph. So here I still have a vertex set V, but my edges now, instead of just being a subset of size 2, they're an ordered pair. So E is a subset of V cross V. This is the Cartesian product between our two sets. So that means instead of having a U comma V in a set, I have a U comma V in an ordered pair. And I think of the edges going from U towards V. So over here, I'll give an example. I'm not just connecting these, I'm now giving each edge an orientation. Something like this would be a directed graph. Now a multigraph, another possibility. Multigraphs allow more than one edge between two vertices. So I'll give you another example picture. I can have two edges between those two vertices, and then I'll put maybe one here and one here, but I could have three edges between those two vertices. So this is not possible with our simple graphs because our edges are a subset of the power set. And the power set only has these two vertices listed once of size 2. So there's only one subset of size 2 that contains this vertex and this vertex. But here, in a multigraph, I'm allowed to have it twice or even 3 times. Your graph could have loops. So a loop is an edge from a vertex to itself. And you can imagine perfectly reasonable that an element might be related to itself. Oh, going off the bottom of the page there. But this is not allowed in our simple definition. Oh, I should draw in my loops. This is not allowed in our simple definition because that would be a subset of the power set of size 1. Right? There's only one vertex involved here. If I have the set u comma u, it doesn't matter that I've listed it twice. That only has size 1. There's only one element in there. So we don't allow loops in our simple graph. The last type I want to talk about are weighted graphs, also sometimes called labeled graphs. And there's some number associated with each edge. So I might have this edge I might label 1, this edge I might label 2, maybe this edge I actually label 0.5, maybe this edge I label pi. I can put any numbers I want. And weighted graphs come up a lot in computer science. You can think of weighted graphs as maybe a distance between these vertices, or maybe a cost to go from one vertex to another. And so you can encode a lot of information in a weighted graph. And then you can ask your algorithm to find something about that graph. So maybe you're interested in what is the cheapest path or the shortest path between two vertices. Maybe your path represents cities, and you want to travel to all of the different cities, and you've labeled the cost to fly from one city to another, and you want to find the cheapest way to go on your vacation. So weighted graphs, also a type of graph, and you can also combine these. So you could have a directed multigraph where you put edges and you allow edges in each direction. Or you could have a weighted graph with loops. That's perfectly fine. So all of these are different things that you might see talked about in different texts for a graph. When we talk about a graph, we're talking about a simple graph unless otherwise stated. So none of these properties. You don't have directions, you don't allow multiple edges, no loops, and in general, we don't consider weighted graphs. Okay, so that's our introduction to graphs. That's the end of part 1. I will see you in part 2.